Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Ellipsometry from paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. In this module, the principle of ellipsometry is explained. Secondly, the expression for amplitude of reflection for S and P polarizations is derived. Third, the various methods to determine the amplitude ratio psi and the phase ratio delta between S and P polarizations such as photometric ellipsometry and null ellipsometry are discussed. Finally, the expressions for psi and delta are obtained for both the photometric and null ellipsometry. Very thin layers of materials that are deposited onto the surface of another material are extremely important for many technological industries. Thin films are widely used to provide passivation, insulating layers between conducting electrodes, diffusion barrier, and hardness coating for wear and tear resistance. The fabrication of integrated circuits consists of deposition and selective removal of a series of thin films. These thin films could be deposited using various deposition techniques including spin coating, vacuum evaporations, sputtering, vapor deposition, and dip coating. To perform the functions for which they are designed, thin films must have accurate thickness, composition, roughness, and other characteristics important to the particular application. These characteristics must often be measured both during and after thin film deposition. Thin film measurement techniques are classified into two categories: optical and mechanical. Mechanical techniques have drawbacks of speed and accuracy, and they always require a step in the film to measure thickness. They are often used to measure the thickness of metallic thin films. Optical techniques determine thin film characteristics by measuring how the films interact with light. These techniques can measure the thickness, roughness, and optical parameters of the film. Optical parameters describe the behavior of light propagating through and reflecting from the material and also provide the information regarding the band gap and composition of material. Optical techniques are usually the preferred techniques for the measurement of film thickness as they provide high accuracy, are non-destructive, and require little or no sample preparation. Ellipsometry is one of the optical techniques which is widely used for thickness measurement. It measures the reflectance at non-normal incidence and at two different polarizations. The name ellipsometry comes from the fact that most often light becomes elliptically polarized after passing through the medium. In ellipsometry, change in polarization state is studied to infer properties of medium. There are already several other methods to measure thickness of the thin films, but ellipsometric measurements have their own advantages. Following are the advantages of ellipsometry to measure the properties of thin films. Firstly, it provides high precision in frequency. Secondly, it provides a non-destructive measurement. Third, it is faster in measurement. Fourth, various optical properties like refractive index and thickness could be measured with high accuracy. Fifth, lower limit of thickness of film can be studied. However, it has disadvantages of high cost, low spatial resolution, and complicated data analysis. Let us now study the principle of ellipsometry. The electric field component of light, which is coming from laser, can be divided into two components, that is, S-polarized and P-polarized component. In ellipsometry, S-polarized and P-polarized light is made to be incident at Brewster angle on the sample as shown in the figure. The final polarized light, which is coming from the sample, is observed. Let EIS and EIP are the incident electric field vectors, and ERS and ERP are the reflected electric field vectors in S-polarized and P-polarized planes respectively. The electric field vectors of incident and reflected light overlap when theta is equal to 90 degree, which is shown in the figure. Let the incident light is polarized at 45 degree relative to EIS. Thus, EIS is equal to EIP since the amplitudes of P and S polarizations are same, and phase difference between the polarization is zero. The only way that there can be a change in the reflection coefficients for two different coefficients of the light can be due to contribution of electric dipoles, that is dielectric, present in the sample. Thus, when the light is incident on the sample, P and S polarizations show different changes in amplitude and phase. Ellipsometry measures the two values, which are psi and delta, that express the amplitude ratio and phase difference between P and S polarizations respectively. If we take sample structure to be simple, which is homogeneous, the amplitude ratio is characterized by the refractive index n and absorption is characterized by the extinction coefficient. These two values can be determined by applying Fresnel's equation. Let the amplitude of reflection for S and P polarization be given by capital P equals tan of phi tan of psi into e raised to power iota into delta, which equals Pp divided by Ps. This can be written as equal to ERP divided by EIP divided by on the whole divided by ERS by EIS. Now, consider an interface of two media having refractive indices of N0 and N1. Using well-known Maxwell's equations, the normal and parallel electric field components of the materials could be derived. Boundary conditions give the reflection coefficients ρ for the electric field components that lie in the plane of incidence I and are normal to its R as ρi equals n1 cos theta naught minus n0 cos theta 1 divided by n1 cos theta naught plus n0 cos theta 1. Rho r is equal to n0 cos theta naught minus n1 cos theta 1 divided by n0 cos theta naught plus n1 cos theta 1. Here, n1 sin theta 1 equals n0 sin theta naught. If there is absorption, then the refractive index can be a complex quantity. Hence, the angles in general are complex. In the present case, the system has three layers having refractive index N0, N1 and N2. First and third layers are separated by a second layer having thickness G as shown in figure 2. For multiple reflection, the component of electric field ER will be ER equals ρ01 plus τ10 ρ12 τ01 e raised to power minus iota 2 beta plus τ10 ρ12 ρ10 τ01 e raised to power minus iota 4 beta plus τ10 ρ12 ρ10 ρ12 τ10 ρ12 ρ10 ρ12 ρ12 τ01 e raised to power minus iota 6 beta, where E is the incident component of electric field and are the reflection and transmission coefficients respectively for a light travelling from ith medium to jth medium. Beta is equal to 2 pi into iota into n1 cos theta 1 divided by lambda, where lambda is the wavelength of incident light. If the second medium is absorptive, then beta can be complex quantity. Amplitude of reflection P is defined as P is equal to ER divided by E. Replace pi as rho and sigma as S. P is equal to ER divided by E, which equals ρ01 plus ρ12 into e raised to power minus iota into twice of beta divided by 1 plus ρ01 into ρ12 into e raised to power minus iota into 2 beta. In particular, for sigma and pi components, p pi equals er pi by e pi, which equals ρ01 pi plus ρ12 pi into e raised to power minus iota into 2 beta divided by 1 plus ρ01 pi into ρ12 pi into e raised to power minus iota into 2 beta. P sigma is equal to er sigma by e sigma, and it equals ρ01 sigma plus rho 1 to sigma into e raised to power minus iota into 2 beta divided by 1 plus rho 0 1 sigma into rho 1 to sigma into e raised to power minus iota into 2 beta. P is equal to P pi by P sigma equals ER pi by E pi into E sigma by ER sigma. This equals rho 0 1 pi plus rho 1 to pi into e raised to a minus iota into 2 beta divided by 1 plus rho 0 1 pi into rho 1 to pi into e raised to power minus iota into 2 beta into on the whole multiplied by 1 plus rho 0 1 sigma into rho 1 2 sigma into e raised to power minus iota into 2 beta divided by rho 0 1 sigma plus rho 1 2 sigma into e raised to power minus iota into 2 beta. This equals rho 1 to pi into rho 0 1 pi into rho 1 to sigma x square plus rho 0 1 pi into rho 0 1 sigma into rho 1 to sigma plus rho 1 to pi on the whole multiplied by x plus rho 0 1 pi on the whole. The entire terms are divided by rho 1 to pi rho 0 1 sigma rho 1 to sigma x square plus within the brackets rho 0 1 pi rho 0 1 sigma rho 1 to pi plus rho 1 to sigma brackets close into x plus rho 0 1 into sigma. Therefore, P equals a times x square plus bx plus c divided by dx square plus ex plus f, where x is equal to e raised to power minus iota into 2 beta. P is a complex quantity, thus it can be written as P is equal to tan psi into e raised to power iota delta, where psi and delta are the real quantities. The main aim of ellipsometry is to determine these two quantities. Equation 7 gives a quadratic equation for x, where the solution x is equal to minus of within the brackets p minus b brackets close plus minus square root of p minus b whole square minus 4 times pd minus a into pf minus c divided by 2 times pd1 minus a, where a is equal to rho 1 to pi into rho 0 1 sigma into rho 1 2 sigma. B is equal to rho 0 1 pi into rho 0 1 sigma into rho 1 2 sigma plus rho 1 2 pi. C is equal to rho 0 1 pi. D is equal to rho 0 1 pi into rho 0 1 pi into rho 0 1 sigma. E equals rho 0 1 pi into rho 1 2 pi into rho 0 1 sigma plus rho 1 2 sigma. F is equal to rho 0 1 sigma. Solving for this gives two values of x. We choose the value with lower imaginary part. Let us next discuss the methods to determine parameters psi and delta. There are two methods to determine these parameters. First one is the photometric ellipsometry and second one being the null ellipsometry. Let us first discuss the photometric ellipsometry. Figure shows the schematic of the setup used for the photometric ellipsometry. The setup consists of two polarizers, one of which is placed before the sample and another one after the sample, which is used as analyzer. the analyzer angle is kept fixed and polarizer angle is changed to obtain the variation in intensity of light at different angles. After linearly polarized light is made to incident on a sample, because two different in refractive index in two different directions, we get an elliptically polarized light. Two methods of finding psi and delta were discussed. The electric field at the detector in terms of Jones matrix formalism can be presented as follows. E naught is equal to a 2 cross 2 matrix with the first row being 1 0 and second row being 0 0 multiplied by another 2 cross 2 matrix where the first row being cos alpha 2 sin alpha 2, second row being minus sin alpha 2 cos alpha 2 multiplied by 2 cross 2 matrix where the first row being row p and 0 and second row being 0 and row s multiplied by a 2 cross 1 matrix with the first row being ei cos alpha 1 and second row being ei sin alpha 1. This equals EP into cos alpha 2 plus ES sin alpha 2, and this equals another 2 cross 1 matrix with the first row element being EP cos alpha 2 plus ES sin alpha 2 and the second row element being 0. I naught is equal to E naught dagger into E naught. This equals cos square alpha 2 into E pi star plus sin square alpha 2 into E sigma star plus cos alpha 2 into sin alpha 2 into within the brackets E pi into E sigma star plus E sigma into E pi star. This can be simplified to be equal to 1 by 2 into within the brackets S naught plus S1 cos 2 alpha 2 plus S2 sin 2 alpha 2 brackets close, where the three Stokes parameters S0, S1 and S2 are given by S0 equals E pi into E pi star plus E sigma into E sigma star, S1 equals E pi into E pi star minus E sigma into E sigma star, and S2 equals E pi E sigma star plus E sigma into E pi star. Using E pi to be equal to rho pi into cos of alpha 1 into EI, and E pi star is equal to rho pi star into cos of alpha 1 into EI, E sigma is equal to rho sigma into sin of alpha 1 into EI, and E sigma star is equal to rho sigma star into sin of alpha 1 into E1 into EI. We can get I naught to be equal to 1 by 2 into S naught into within the brackets 1 minus cos 2 psi prime into cos 2 alpha 2 plus sin 2 psi prime into cos delta into sin 2 alpha 2, where psi prime is such that tan of psi prime equals tan of psi divided by tan of alpha 1. Comparing, we get cos 2 psi prime equals minus S1 by S0 and sin 2 psi prime into cos of delta equals S2 by S0. We can see that I naught at 0 degree is equal to 1 by 2 into S0 plus S1. I naught at 45 degrees is equal to 1 by 2 into S0 plus S2. I naught at 90 degrees is equal to 1 by 2 into S0 minus S1. If we choose tan alpha 1 is equal to 45 degree, then we get cos of 2 psi is equal to I naught at 90 degrees minus I naught at 0 degrees divided by I naught at 90 degrees plus I naught at 0 degrees. Sin 2 psi into cos delta will be equal to 2 I naught into at 45 degree minus I naught at 90 degree minus I naught at 0 degree divided by I naught at 90 degree plus I naught at 0 degree. Hence, with three experimental inputs, we can determine psi and delta. Another way of determining the Stokes parameter is S naught is equal to 2 pi into within the brackets 2 times the integral going from 0 to pi by 2 I naught of theta into d theta plus the integral going from pi by 2 to pi I naught of theta into d theta on the whole divided by 3. S1 equals minus of integral going from pi by 4 to 3 pi by 4 into I naught of theta d theta plus the integral going from 0 to pi by 2 I naught of theta d theta plus the integral going from pi by 2 to pi over I naught of theta d theta on the whole divided by 3. S2 equals 3 times the integral going from 0 to pi by 2 I naught of theta d theta minus the integral going from pi by 2 to pi I naught of theta d theta divided by 3. Let us now discuss the null ellipsometry. In this technique, along with the polarizer and analyzer, a quarter wave plate is also used as shown in figure 4. From the figure 4, it can be seen that the incident light passes through the polarizer, making the light linearly polarized. After passing through the compensator, the light becomes elliptically polarized and then made to pass through the sample. For some polarizer angle, the elliptical polarization produced by a sample can be compensated by the quarter wave plate giving a linearly polarized light after passing through the sample. This light can be made to obtain zero intensity at some angle of analyzer if the values of a sample are assumed to be psi is equal to 45 degree and delta is equal to 90 degree, then the intensity of detected light will be 0. From John's formulation, as shown in figure 5, L out is equal to AR into A into SR into minus C into C into R into C into R into minus P into P into Ln. We obtain EA to be equal to P pi into within the brackets cos of C into cos of P minus C minus rho 1 of C into sine of C into sine of P minus C bracket close into P sigma sine A into within the brackets sine C into sine of P minus C plus rho of IC into cos of C into sine of P minus C. Here, rho 1C is the phase shift by compensator e raised to the minus iota delta. The rotation angle for quarter plate is 45 degree and phase shift is 90 degree. Here, for we put zero intensity, that is EA is equal to 0, C is equal to 45 and delta is equal to 90. So we get P is equal to tan psi into e raised to iota into delta, which equals P pi by P sigma and is equal to tan of A into e raised to power iota into within the brackets minus 2p plus 90. From here, we can get psi delta values which are determined by A and P, and we get psi is equal to minus A, where minus A is greater than 0. Delta equals minus 2p plus 90 degree. For psi is equal to A, where A is greater than 0, delta equals minus 2p minus 90 degree. Similarly, two solutions for C is equal to 45 degree are obtained. Therefore, the four sets of P and A give zero intensity, which gives the thickness of thin films. Thickness of the film in null ellipsometry can be determined by keeping the compensator at 45 degree and changing the analyzer and polarizer angle to obtain minimum intensity. So students, let us now summarize what we have learned in this module. In this module, the principle of ellipsometry is explained. Secondly, the expression for amplitude of reflection for S and P polarizations is derived. Third, the various methods to determine the amplitude ratio psi and the phase ratio delta between S and P polarizations, such as photometric ellipsometry and null ellipsometry, are discussed. Finally, the expressions for psi and delta are obtained for both the photometric and null ellipsometry. Thank you students for your attention.